In the name of Allah, the most gracious, the most merciful, all praise is due to Allah, and peace and blessings be upon His messenger, our Master Muhammad, and upon his family and companions altogether. Now, as for what follows, by time indeed mankind is in loss, except for those who have believed and done righteous deeds. And they enjoined one another to the truth and enjoined one another to patience. We will begin with you in explaining a new chapter of protection, which is the overcurrent and air fault, but in a practical way that touches reality and in an enjoyable and interesting manner. So stay with us. They are the oldest, most famous, and most widely used protective devices in substations. This is because any fault that occurs results in an increase in current, which refers to the current flowing through various equipment like cables, transformers, motors, and others, exceeding the designed value for that equipment. The overcurrent relay monitors the current value. If current exceeds the setting or stinging value, the relay decides to trip or start. We must discuss reasons for current increase. Is any current increase a fault causing disconnection? No. This is the relay challenge. How do relays distinguish 10 amps as a fault or natural increase? Relays must also distinguish 0.1 amps as a fault or natural increase. Consider any current increase a fault causing disconnection. Of course not, this is the relay challenge. How can the relay tell if 10 amps is a fault causing disconnection or a natural increase not causing disconnection? Moreover, the relay must tell if 0.1 amps is a fault causing disconnection or a natural increase. The overcurrent relay should not operate when 1. During startup current. 2. When current exceeds permissible levels briefly. This fault should cause disconnection. The overcurrent relay should not operate during startup current. It should operate when current flow is considered an increase. The overcurrent relay must not operate in the following cases. 1. During the passage of starting current resulting from the start of operation. 2. Increase in the permissible current to operate the equipment for a specific period of time, or during the transient current to which the networks are exposed momentarily. The overcurrent relay works during normal and increased current flow. It must distinguish between fault and overload currents to make correct decisions. Engineers program the relay to differentiate these currents. Understanding why fault current increases is crucial. Rather, the overcurrent relay must distinguish between the fault current and the overloading current, because the overcurrent relay must make the appropriate decision in the appropriate case. In order for the relay to be able to distinguish between them, engineers must distinguish between them before the relay, because the relay is nothing but a device that contains a group of processes that the engineer programs. In order for the relay to understand the difference between them, we need to delve deeper to identify the factors influencing the increase in fault current. Or we might ask another question. Why does the current increase when a fault occurs? The current value increases when a fault occurs because the short circuit condition creates a new path with low resistance, effectively bypassing the load impedance, which is relatively high compared to the generator and line impedance. Thus, the current has two paths. The first path is the short circuit path, and the second path is the load impedance path. As is known from Ohm's law, the higher current flows through the lower resistance. But one might ask, how did the current become large? Before the fault, the current was flowing through the load impedance, and after the fault, the same current is now flowing through the short circuit. So where did the increase in current come from? The higher current flows through the lower resistance. But one might ask, how did the current become large? Before the fault, the current was flowing through the load impedance, and after the fault, the same current is now flowing through the short circuit. So where did the increase in current come from? The answer here is that when the load impedance value is lost, the current does not remain the same. Instead, it increases. This is because the voltage will supply lower resistances, and the fewer the resistances or the lower their values, the greater the current becomes. In addition, all the currents in the network will go to feed the fault area. We can also look at the increase in current when a fault occurs from another perspective or philosophy. What happens if we add another load similar to the load impedance in parallel so that it receives the same voltage? It's important to note that any added loads must be in parallel, and increasing the loads means a decrease in resistance in this case. The generator will create more current to power the necessary added loads. The increase in current is due to a decrease, as equivalent impedance is one resistance divided by load number. More loads mean lower value and higher current. Adding infinite loads makes load approach infinity. Anything divided by infinity is zero. If value nears zero, generator current is zero. Any value divided by zero is infinite. So current is infinite, ignoring generator and line impedance. So if we were to increase the load to infinity, anything divided by infinity would have a value of zero. Therefore, if the value approaches zero, the current supplied by the generator would also be zero. And any value divided by zero is infinite or approaches infinity. So the current value here is infinite, of course, neglecting the generator impedance and line impedance. Thus, a short circuit simulates adding an infinite number of loads in parallel. Adding infinite loads or reaching a short circuit limit can theoretically result in drawing infinite current from the generator. Of course, the generator cannot supply this amount of current, so its speed increases towards infinity to keep the voltage constant at the load. Generator impedance and line impedance. A short circuit is like adding an infinite number of loads in parallel. The addition of infinite loads or reaching a short circuit limit can theoretically result in drawing infinite current from the generator. The generator cannot supply this amount of current, so it speeds up infinitely to keep the voltage constant at the load. We know it is more complex, but we simplify to understand better. Also, the location of the fault is the first factor affecting the value of the fault current. Clearly, the farther the fault is from the relay, the more resistance, the lower the fault current. Closer faults mean less resistance. We must understand the location of the fault is the first factor affecting the value of the fault current. Clearly, the further the fault is from the relay, the greater the resistance the relay sees, and thus the lower the fault current value. In contrast, the closer the fault is to the relay, the lower the resistance the relay sees, increasing the fault current value. This is why detecting distant faults is hard. The current increase is slight and often unnoticed. The second factor affecting the value of the fault current is the fault resistance, or voltage resistance RF. The first factor affecting the fault current value is the fault location, and the second factor is the fault resistance. Higher fault current explains why distant faults are hard to detect. The increase is slight and often unnoticed. The second factor affecting the value of the fault current is the value of the fault resistance, known as voltage resistance, symbolized by RF. So the first factor affecting the fault current value is the pole fault location, and the second factor is the fault resistance. So, when an overhead line falls to the ground and there is a short circuit, the fault current will flow from the relay location to the fault location through the Z line fault. Then, the fault current may pass through another resistance called the fault resistance, symbolized by RF. This resistance RF is affected by the type of soil, whether it is clay, rocky, sandy, or otherwise. It is also influenced by the presence or absence of a spark at the fault location. Therefore, if we take into account the value of the fault resistance, the fault current can be expressed as follows: I fault equals versus. It is affected by the type of soil, whether it is clay, rocky, sandy, or otherwise. It is also influenced by the presence or absence of a spark at the fault location. Therefore, if we take into account the value of the fault resistance, the fault current becomes as follows: I fault equals, on the Z-line fault, this equation explains why it is difficult to detect faults with high resistance, as the increase in fault current is very slight. So, we conclude from the first and second factors that it is difficult to detect faults that are far from the source or faults that occur due to high resistance. There was an incident where a line fell in the desert of one of the countries, and the line remained operational even after it fell because it couldn't sense the very low fault current. We noticed this in this video. The fall of a high voltage line in the dry desert areas with high resistance led to the appearance of a low fault current that the protection device missed. As a result, the line remained operational, killing many creatures. Thus, protection device sensitivity is crucial. Understand that fault resistance RF comes from the arc and tower grounding. Tower grounding resistance varies from under 1 ohm to hundreds. Arc resistance is calculated per foot, and higher fault current lessens its effect. The fault resistance RF is due to the electrical arc generated by the fault, in addition to the grounding resistance of the tower. As for the resistance resulting from the grounding of the towers, it varies widely, ranging from less than 1 ohm to values exceeding hundreds of ohms. The resistance of the arc is calculated using one of these approximate equations, and all these equations calculate the arc resistance in ohms per linear foot of the arc length. It's important to note that the higher the fault current, the less significant and limited the effect of the arc resistance, as is clear from the equations. The third factor affecting the value of the fault current is the strength of the power supply. The first factor is the location of the fault, and the second factor is the value of the fault resistance. The third factor is the strength of the power supply, which is expressed by the low impedance of this source. The lower the impedance of this source, the stronger the source is, and it has the capacity to feed the fault. If we imagine that the feeding station has 3 generators and all 3 generators are operational and connected in parallel, then the equivalent source impedance for the 3 generators together is XS divided by 3. Therefore, the total impedance from the source to the fault location will be small, and as a result, the fault current value will be large. In this case, the source is referred to as a strong source. It will be small, and therefore the value of the fault current will be large. In this case, the source is called a strong source.